We saw it in 2017. Real bad, okay. Really?
Yeah, my mom.
Yeah, that's cool.
All right.
Big city, so.
It is so hot.
Honestly, it's not. Everyone knows everyone.
Okay.
Yeah. My best friend's mom, we walked. Me and him were getting breakfast one day, and people kept coming up to him and being, "Oh my God, how are you?"
That's good.
Why is it not showing? Please. All right. So we were looking at variation of parameters. Just to recap, if you have a differential equation that has non-constant coefficients, so these P of t and Q of t may not be constants anymore, and then you might, have a non-homogeneous, so you have some kind of thing on the right-hand side. We've looked at non-constant coefficient different second order, but if it was an Euler equation. And we also did reduction order, which actually solves any kind of second order differential equation that's homogeneous, linear. So these don't follow the so these coefficients don't follow the Euler format. But if it's homogeneous and you're given one homogeneous solution, then you can solve the full general homogeneous solution. But what if you have a non-homogeneous right-hand side? You need to build a function, you need both your homogeneous solutions. So you need x1 and x2. And you're going to say kind of like reduction of order, but you're just going to have a combination of these two. So you're going to have like V1 times your first homogeneous solution plus V2 times your second homogeneous solution, where your V1 and V2 are some functions of t that you're going to force to satisfy this differential equation. But that only gives you one condition, but you have two unknowns. You have V1 and V2 that you don't know. So you'll need two conditions. And I just threw this out of nowhere, kind of. I just said, just assume this. That's like, you're free to choose a second condition so long as that it works. And this one does end up working. It does also simplify the second derivative, because once you set this to 0, then you only have these two to do the product rule on. Otherwise, you would have had 8 terms for your second derivative. And some of those terms would have had V1 double prime, V2 double prime. This, I actually decided that I'll show you that this I will show why this makes sense. This comes out naturally when we solve systems of differential equations. I'm going to convert this second order equation to a system of first order equations, and then show you that you get these two things that are in blue boxes from analyzing an equivalent system, an equivalent problem that transforms this to a system of first order equations. So for now, we're just going to say we have two unknowns, V1 and V2, so you need two equations for two unknowns. And we're just going to use the one that will obviously be used is the one that comes out of plugging it in and forcing it to satisfy. That's this bottom one. This one's one that I just said we're going to assume along the way. So that's a system of two equations for the unknowns are V1 and V2 prime. And so I have written that here. For this problem, we have an Euler equation on the left-hand side. So we can actually build our two homogeneous solutions. So we have those two, and then we propose that the general solution for this non-homogeneous is the combination of those two added together with V1 and V2 prime. V1 and V2 we're still going to try to find. But we're going to have to, based on forcing it to satisfy this differential equation and also this other assumption that I'm just throwing out there, we need to have this system satisfied. So our x1 and x2 are t and t cubed. So those go into x1 and x2. x1 prime and x2 prime are just the derivatives of those two. So you have this. And what I'll do is I'll just take the first equation, and we can just solve this system just by hand using our traditional algebraic, So our unknowns are V1 prime and V2 prime. And what we can do is we can just solve for V1 prime. So we'll move this to the other side, and it'll be V2 negative V2 prime. But then it'll be t cubed. We're going to divide by t, so it'll be t squared. So that's just the first one. And then you're just going to take that and plug it in. This is V1 prime. So this is the substitution method. You just plug it into here. And so if this is coming from your first equation, and we can say that the second equation is this one right here. And I'm just going to write that down here. Say the second equation Yeah, did I do
Should it
something?
be like 4t to the 7th power? For
Well, so the thing is, you have to remember that for this right here, we ended up deriving these equations. Actually, like this equation is fine, but this equation is contingent on this f being after the first term has been divided out. So we were using the convention that the first whatever used to be in front of this must have been divided out. So we only have a 1 in front of this x double prime. So this t squared has to divide this. It's like as if you just took this whole thing and divided the whole equation by t squared, and that's the f of t that you use. Yeah, that's important. And so we have this second equation right here, and we're gonna plug in this, substitute this in. So we're gonna have negative v2 prime t squared plus the rest of it is equal to 4t to the 5. And then you can consolidate. So this is like 3t squared. This is 1t squared. So you can consolidate, and this just becomes 2 t squared v2 prime is equal to the 4t to the 5. And then you can just divide through by 2t squared. And you'll end up getting that v2 prime is equal to 2t cubed. And then you're just going to integrate this. The reason why we're integrating this is, well, actually, even before I do that, you can just, let's do this. So this is our v2 prime. And then our v1 prime is up here. So I'll just like rewrite that down here. Say that from the first equation, we got this. So we now can substitute back in the v2 prime, and we'll end up getting that this is equal to, because it's 2t cubed, and then this is a t squared, so it's going to be minus 2t to the 5. And then you can just integrate both of these, because these are v2 prime and this is v1 prime. So we've successfully used the two equations to find the derivatives of the things we want, but we got to integrate both of these to get the v2 and the v1. So the integral of this is going to equal t to the 4 over 2 plus integration constant. I'll use C2 for this because this is for the V2 term. And this one is going to integrate to negative t to the 6 over 3 plus the C1. And so now you've got your V1 and V2s. So all you're going to do is you just say that your solution is this red thing that we've already written up here. So I'll just copy that and say this is our solution with the V1 and V2s plugged in now. Let's see. So our V1 is this guy. And our X1 is, I'll just say X1 is T, right? Because that's right here. We've said that first homogeneous solution is T. Plus we have the second one, which is V2. And the second homogeneous solution is T cubed. And so if you actually multiply this out, so you get this t times this, t cubed times this, it's going to be a t to the 7th for both of them. You have a half minus a third, which gives you a 6th. So it's going to be t to the 7 over 6. And then you have the C1t plus the C2. I'm just multiplying it out like this so that it's very clear to what is going on? That this is your particular solution right here. And this is your homogeneous solution. Okay, so this is using variation of parameters to solve an Euler equation that's non-homogeneous. And we end up using this system. This system is derived from forcing this proposed solution form to satisfy the differential equation. And the top one was just me saying that we're just going to use that assumption because we need two equations for two unknowns. And I'll justify the first one later. So that's the process. It's actually just solving a system of equations, linear equations, for the unknowns v1 prime and v2 prime, and then anti-differentiating those to get your v1 and v2. So this actually is just solving a system of equations, and there is something called linear algebra that can help you simplify that process. So I'll introduce a couple of linear algebra things so that it'll be easier for us to solve these. In the end, there's going to be just a straight up formula that we could use. So I'm just going to copy this system. I mean, you could solve it the good old-fashioned way that we just did, but you may find it easier. And also, we're going to talk about different things that are involved, like, that are going to be involved in this process later as well. So it's good to maybe show you this. So we have these two equations. And if you, in general, want to come up with a formula that gives you v1 prime and v2 prime, you can basically do the elimination method. If I wanted to, say, eliminate v2 prime. So there's a v2 prime up here and a v2 prime down here. And I want to eliminate those two. Well, this one has an x2 prime. So I'm just going to multiply this by x2 prime. I'm going to multiply this by x2 because that's what the other one has. And then you can just subtract those two. So I'll just label this as 1 and this as equation 2. And I'm going to say, suppose you want to eliminate the v2 prime term. Then you can just say 1 minus 2 with these two equations. If you do that, you'll end up getting this v1 prime x1, and then this v1 prime x1 prime. They're not the same because this one's got no prime on it and this one has a prime on it, but they do both have a v1 prime that's common. So I'll just say that just ends up becoming v1 x1. Well, it's x1 times the x2 prime, because this, you got to think this orange gets multiplied. It's going to be x2 prime minus this, and this is being multiplied, so it's going to be the x2 gets multiplied, and then there's an x1. Is going to equal, so this term right here, those cancel by design, because this one's going to be v2 prime x2 prime, and then it's also going to be v2 prime x2. Those are going to subtract out. That was the reason why we multiplied the first one and the second one by this. This one, this times 0 is nothing, subtracted by this, so it's going to be negative f x2. So our v1 prime is just negative f of x2 all over this thing right here. Okay. And that's the formula for v1 prime. Like, you could just, f, that's like your f that you just read off after you divide out the first term. And then x2 and x1 because those are your first two homogeneous solutions. So this gives you a straight up formula for v1 prime, and then you just anti-differentiate that. And then you'll get your v1 just like we had here. So, we could actually, we'll do it with this problem, this formula with that problem, and see that we get the same thing. Now, we still need to find v2 prime. So what I'm going to do is revisit the first equation. It doesn't matter which one you use, but if you use the first equation, and if you use the first equation, you can look at substituting this v1 prime into this v1 here. So it's going to be literally all this. Times x1. So just say x1. So there's an x1 here. So I'm just going to say x1 here. And then you're going to add to this your v2 prime, x2. And this has to equal 0. So you just subtract both sides. So you got your V2 prime. I'm gonna actually do this in one thing where you're just gonna add this to both sides. So I'll remove the minus in a second here. So it's on this side now without a minus after you do that. But then you would have divided by x2, right? So that means that this x2 is gone, and then you'll just have this. So this is the formula for V2 prime. And then so you just anti-differentiate those two. Okay, so that's good enough. I wanted to mention that you could also notice a connection with, so this right here, if you were to write it as a matrix equation, so the way it works is, I have to introduce how to do matrix multiplication, but the V1 prime and V2 prime are your unknowns. Those are your solutions. So the coefficients are actually, even though the way this is written, it looks like the coefficients are written on the second entry here, but the coefficients are actually x1, x2, x1 prime, x2 prime. And then our solutions, the unknowns are the solution vectors, what they call it is v1 prime and v2 prime. Okay, and so I want to say this is how you translate this thing right here into a matrix. This is the same thing as that, and it's the same because you can actually use how matrix multiplication works is going to, by design, make this the same. The way the matrix multiplication works is this thing is equal to, is like a matrix. You have like a 2x2 matrix multiplied by a 2x1 matrix, which is just a vector. And the way they multiply is you go like left on this matrix here, and you go down here. So you start at the top left here and multiply it with this. Okay, that's going to be x1, v1 prime. And then you're going to add to it, you're going to go to the left, because this arrow is going to the left, and you're going to take this entry, but you're going to go down on this side, and you're going to multiply those two. So you're going to have x2, v2 prime. Okay, and then you just go one more row down, and so you're going to start again with the left. You're going to say, I'm going to multiply with this times this. That gives you this entry, which is just going to be x1 prime, use green, x1 prime, v1 prime. And then you're going to add to this. You're going to move one more to the left on this side. So you're going to do this and then go down one. And so those two get multiplied. And you're just going to say that this is going to be x2 prime, v2 prime. That's how matrix multiplication works. And if you look at it, that's exactly the same as this right here. So you have v1, I mean, they're switched, but this is x1 and v1 prime, x1 and v1 prime, x2 and v2 prime, x2 and v2 prime added together. And then here is the same thing. So that's how we've successfully translated this into a matrix. They have names. This is called the coefficient matrix to this system. And this is called the solution vector. It's also true that anytime you have I'll just use like, I don't know what color, I'll use blue. You have a 2x2, I'll use blue, 2x2 matrix multiplied by a 2x1. We use row as the first when we say 2x1. And if they can only be multiplied if these entries are the same. So the middle of these two, so the last of this and the first of these are 2, so that works. And then it'll give you it'll spit out a matrix of the size 2, 1, which is the outer. So it's going to be 2, 1. This is 2, 1 because really we're adding 2 things off for the first entry of the row, and we're adding 2 things for the second entry of the row. And that's exactly the two rows that represent the left-hand side of this equation. But I wanted to point out why are we doing this? We have a coefficient matrix here. So if you look at this coefficient matrix, I'm going to define some other thing here. So there's something called the determinant of a matrix. So I'll just write that down here. The determinant of some matrix, if it's a 2x2 matrix. So I'll just say determinant of A, B, C, D is defined as A times D minus B times C. So it's really just taking these two multiplied together minus by these two multiplied together. Okay, so let's look at the coefficient matrix. So this coefficient matrix, and let's take the determinant of this coefficient matrix. So the determinant of this coefficient matrix is called the Wronskian. And this coefficient matrix for this system happens to be of a very specific form. It's the first homogeneous solution and the second homogeneous solution. And then the next row is just their exact derivatives, right? So that's actually a very special kind of determinant. It's the determinant of your two homogeneous solutions and their derivatives on the second row. Well, the determinant is just like this formula. It's going to be x1 times x2 prime minus these entries. So it's going to be x2 times x1 prime. Okay, so if you look at these denominators, make them purple so that's very obvious. These are actually exactly the determinant of the coefficient matrix. So you see x1, x2 prime, x2 minus x2. So these are the determinant of the coefficient matrix, which is the Wronskian. So I'll just say this is called the Wronskian. So the formula is even more simplified to just negative f of x2 over the Wronskian, which is I mean, you could build the coefficient matrix, but it's going to be of this form, x1, x2, x1 prime, x2 prime. So your v2 prime is going to be fx1 over the determinant of this, which is the Wronskian. This gives you a formula for your x1 and x2. Okay, so again, x1 prime and x2 prime. So this again is x1 prime. So I'll put a green box around this. And this is our x2 prime. v2 prime, did I say x? The v2 prime and x1, v1 prime. Okay, so we have, this is your formulas for v1 prime and v2 prime, and then you take the antiderivative of those. So this is maybe easier to just use this formula directly because you know your x1 and x2. So you know your x1 prime and x2 prime, and you also know your f. So you can actually do this rather than doing all this work, which is classic algebra. So let's apply that to the same problem. Oh, actually, well, let's skip, there's a few things. Let's apply that to this, this problem right here that we just did. So the problem we just did, what do we have? It's going to be, I'll just copy the first part. So I'll just say we have all the same initial equation and the same homogeneous solution. So we'll just use that. And what I'm going to do is just say we have that. So we have our x1 and x2. Our x1 is t. Our x2 is t cubed. Our x1 prime is 1. Our x2 prime is 3t squared. And what is the Wronskian say? The Wronskian says I just take the determinant of the matrix that's built off of the x1, which is just t. x2 is t cubed. 1, 3t squared. This is the determinant of this. Okay, so then that's just going to mean that it's equal to, you're just going to take these entries and multiply. So 3t cubed minus a t cubed. So your Wronskian is 2t cubed. Okay, and then we're going to use those formulas. V1 prime is equal to negative F x2 over the Wronskian. If we scroll up, you'll see that this was the formulas for them. And this one was F x1 over the Wronskian. So our F, again, we're going to have to use the F that comes out of dividing everything out. So here, our F is going to equal the 4t to the 7th, but then divided by the t squared. So it's really 4t to the 5th. Okay. So we're going to have negative 4t to the 5th. x2 is t cubed. The Wronskian is 2t cubed. So the t cubed cancels the 4, so negative 2 t to the 5 is going to be the v1 prime. This one is 4t to the 5. x1 is t. The Wronskian is 2t cubed. So you have, at the end, you'll have the t cubed and so this is a t to the 6, so it'd be t cubed, so 2t cubed. And you just integrate. Integrate. And you'll end up getting that V1 is equal to negative 6, no, t over 6, t to the 6 over 3. Because if you pull this down, you get negative, it's fine, plus C1. And then V2 is going to equal t to the 4 over 2 plus C1, C2. And then the rest is the same. So like you'll notice that that was exactly the same thing that we got for, I'll just copy this whole thing. That was the same thing we got earlier by just traditional high school algebra using substitution method. Just copy and paste that in. Delete all this. So if you notice that this right here is right here, and this right here is right here. So this is using Cramer's rule to find your V1 prime and V2 prime. Okay, so let's scroll back up. So for people who have taken linear algebra, I mean, so that's enough. You don't have to know this little thing, but I wanted to mention that this system right here, let's just grab it from here. Right. Written in matrix form is the same thing we just said before. In matrix form, it's going to be your x1, x2, x1 prime, x2 prime. And then your solution is going to be your V1 prime and your V2 prime. This is exactly copying this right here, this red stuff right here. So that's the left-hand side. Turns out the right-hand side is just a 2x1 vector, or 2x1 matrix, which is just, people call that a vector if it's just a single entry. I'll just use F. You have this. Okay. So again, this is like our A. I'll call this like, so in linear algebra, people might call this your A. This might be your solution vector V. And this is like your right-hand side. So this, people might call this your B or something like that. But like if you wanted to find your solution, V1 prime and V2 prime is your solution vector here. Like, what do you do? Does anybody, I mean, this is not required knowledge because you don't have to know linear algebra, but people who took linear algebra, what would you do to find the V vector? And you do the what? So
two and you want to be a two, and you're making this.
Oh, you're doing like Gaussian elimination or something. Okay, well, we'll just do the inverse matrix. So if you have a v vector times the b is equal to the b vector, this is just the assuming that the inverse exists. Okay, so the A inverse exists. You just compute the inverse matrix, and you'll get that your solution is this. Now, the assumption that the inverse exists is a little deeper. The x1 and x2 actually have to be linearly independent for that to be true. And we're going to go into that in the next section. The existence of a solution here without any issues requires that your x1 and x2 can't be anything. They have to be two homogeneous solutions that are not linear combinations of each other. And all the techniques we've been doing so far guarantees that x1 and x2 are linearly independent, but I'll go and look into that because I just kind of skipped over that. And therefore, this inverse matrix will always exist because this matrix will be non-singular, and we'll have no issues. But if you actually do, people may remember the inverse matrix for a 2 by 2. So if this A inverse matrix is going to be equal to, let's suppose you have, this is your A, B, C, D, and you're just trying to invert it. The way it works is you have 1 over the determinant of A, and then you say that it's going to be multiplied by the matrix D, negative B, negative C, and A. It just flips these A and D and then puts the negative on those two. So using that, this will be 1 over, what is the determinant of A? It was a very special thing I just named. This is a matrix with it's the Wronskian. Or I don't know what you just said, but it's the Wronskian. I just assumed that you said the Wronskian because this is the entries of x1, x2. So this determinant of A for our particular matrix here is actually the Wronskian. And then this is going to be multiplied by the entries x2 prime, negative x2. And then it's going to be negative x1 prime, and then x1. Because all you're doing is you're flipping these two. So this x1 goes down, x2 goes there, and then we're putting negatives on these. And then you can say that this is being multiplied by 0f. And then let's just move this over. Okay, so then you have 1 over the Wronskian times, let's do matrix multiplication on this. So it's going to be this times 0, which is 0, plus this times this, so it'd be negative x2 f. Then this times this is 0, this times this is x1 f. So in the end, we have, what does this mean? This means that your top entry is your v1 prime. So your v1 prime is equal to negative x2 f over the Wronskian. Wronskian is just going to be a number. And then your x2 prime is x1 f over the Wronskian. This is exactly the same formulas for x1 prime and x2 prime that we had just gotten up here. So x1 is negative f, and then x2w, so negative x, x2w. All that, okay? So it just is consistent with if you were to just take a system of equations, if it's only a equation of two, it's just a 2 equation, it's a 2 by 2 matrix, so the inverse is very easy to compute, so you may just go ahead and do that. That's just using the power of linear algebra rather than just using like just normal high school algebra to solve this, okay? All right, so there is something nice in general about this process, so I'll just copy this right here. So there's I'm going to go into something called the Green's function. So you have your v1 prime and v2 prime are these. Now I want to emphasize that these actually are all functions in general of t. So I'll just write this as negative, x2 of t, f of t. They're all functions of t. Even the Wronskian is a function of t. We just saw one earlier, right? What was it? Right here. The Wronskian for this was 2t cubed. which is a function of t. It may just be a number sometimes, but in general, it may be a function of t. Your v2 is also going to be functions of t. F of t. And the Wronskian is also function. So what's the general process? You have v1 prime and v2 prime. You're just going to integrate this. Okay, and so you'll have a v1. And without knowing what these all are, I'm just going to use just a definite integral. So I'm going to say, using fundamental theorem calculus, I can say that I can integrate from some initial t to current t of this thing. And what I'll do is, it's good convention to use a different variable. So for the integration, and I usually used s in our class whenever we do this. So I'll do s. This becomes more important for this kind of problem because you got to keep track of which one's the integration variable and which one is the actual variable. So that's fundamental theorem. To just leave it as a definite integral, you're going to integrate from t naught to t of this guy. But then I'm going to replace all the t's with s's. And this is ds, and another integration comes. Okay, and what did we say? The general solution, Rx of t, is built off of your v1 x1 plus your v2 x2. Okay, let's just plug those in directly. So we have the integral is all of this guy is v1. Multiplied by x1. Plus, you're going to have, and I'll make it very clear here that x1 is a function of t. Okay, it's your first homogeneous solution. And then you're going to add to this, your v2 is this entire integral expression. Plus c2 times the v2 is also a function of t. All right, now I'm going to combine, because these integrals are over the same intervals from some initial t naught. You know how this used to be like our a, but we always plug in the initial t naught in there. So we'll have this. So it combines to an integral of t naught to t. There is a w, the Wronskian is the same in both of these. There's also an f of s that's the same in both of these. So the only thing I'm going to do is you have an x1s multiplied by an x2t. So x1s, x2t. Subtract, I'm writing this first because this one's a minus. And I'm going to do x2s, but this x1 gets multiplied. So it's going to be x1t all over. The Wronskian is common across both of these, and they both have an f of s. And then the rest of it is just c1 times this one, plus your c2 times x2t. Okay. All right. So this term in the integrand, this is the integral kernel of the integral here. That's what they call this. This one is actually in general a function of both s and t. This is why it's really important that you remember to label your integration variable as something else, because then it'll look like you only have t's, and it's not clear which one is the integration variable and which one is actually the variable. So this actually is a function, capital G, of s, comma t, function of both s and t, and this is called the Green's function. Okay. And it has is a very special property, which is described at the top here. So the thing is, this is the general solution for this non-homogeneous second order equation. Now, let's say everything about the equation stays the same, but your forcing changes. That means that if your left-hand side stays the same, so basically you have an equation like, this right here, and you have 4t to the 7th here, but let's say all you do is you change the right-hand side, you're only changing the f. You're only changing the forcing. Everything else is still the same. So the homogeneous solution will still be the same. So your x1 and x2 will still be the same. So your Green's function will still stay the same because your x1 and x2 and your Wronskian, which is built off of your x1 and x2 as well, are all going to stay the same, but only your forcing will change. So if you have a Green's function for your equation. So in general, your Green's function for your differential operator, then your solution form stays the same with only the forcing changed, with only your f of s is changed. So this is just describing, use fundamental theorem calculus, combine integrals to obtain a solution. And it turns out that the solution appears to be looking like you have a sum or integral of all the forcings. This f of s is being integrated across all time from initial until present. And this Green's function acts like a weighting function. It's like a weighting function. It's called the influence function. So it weights the contribution to the solution or the response at the present t due to forcing at all preceding times. And an advantage of knowing the Green's function is, again, like if the system is still the same, but only the forcing has changed, then you can use that Green's function times the new f of s and integrate it across all time. We'll do an example of that, but that's a nice physical that comes up in a lot of other fields. So I wanted to bring up that. So let's get more familiar with the variation of parameters. This right here is a non-homogeneous equation, a constant coefficient, but the right-hand side has an issue. So you can't use the method of undetermined coefficient because the method of undetermined coefficients, although the left-hand side is fine because you have constant coefficients, you have a right-hand side that's not of the form we know, which is cosines and sines or exponentials. So we have to use variation of parameters. But the homogeneous, again, with the variation of parameters, you have to have both the homogeneous 1 and 2 solutions. But you can find that easily with this because it's just the characteristic equation. Because it's the right-hand side is still a very simple equation. So you're just going to get that r is equals to plus or minus I. And therefore, your homogeneous solution is equal to C1 cosine of t plus C2 sine of t. And then what do? We just list the x1 is equal to cosine of t. Your x2 is your second homogeneous solution, which is sine of t. Your x1 prime is just the derivative of cosine, it's a negative sine of t. Your x2 prime is your cosine of t, okay? We should be able to compute the Wronskian from this because it's just the determinant of these entries. So I'll just, it's like, think of this as a matrix. It's already written like a matrix. I wrote it like this so that you can just see immediately that you just do the determinant of this thing. So the Wronskian is equal to this times this is cosine squared t minus this, but there's a negative, so it's a plus sine squared t. But what is that? That's just 1. So the Wronskian is just 1 for this one. And then we're just going to grab our handy formulas that we just had up here for V1 prime and V2 prime. And W is 1 because the Wronskian is 1. The F is secant t because this has no, you don't have to, this was already 1 in the front. So F is equal to secant t. So you're just going to write this out. It's going to be negative secant of t times our x2 is sine of t divided by 1 is just not to write that. This is going to equal negative sine of t over cosine of t, which is just negative tan. But I'm going to write it this way because I don't know if you guys know the derivative integral of tan. So I'll just have to do that by hand. This one is going to be, again, f is secant times x1 is cosine of t. This one's super nice because secant and cosine just multiply out to be 1. So the integral of that one is so super easy. Integrate. The v2 ends up becoming just t plus c2. This one you have to integrate as well. So the integral of negative tan, you want to use substitution. So I'll just say, you're just going to say that the substitution is going to be, I'll use the cosine of t. That means that your du is equal to negative sine of t, which is perfect because that shows up right there. So you have that v1 after this sub is going to equal the antiderivative of du over u, which is just equal to the ln of u, but I'm just going to replace the u as cosine. Ln of absolute value of u cosine is that plus c. Okay, so that's the antiderivative of negative tan. Don't think that it's secant squared because that's actually the derivative of tan, but the antiderivative is not. So your solution in the end is going to be a combination of your v1 x1 plus v2 x2, which ends up becoming, the first one is this one. And then that's going to be multiplied by our v1, x1 is cosine of t, plus our v2 is the t plus c2. I'll just write that, t plus c2, multiplied by sine of t. And if you multiply this out to try to get the particular solution and the homogeneous solutions to separate out, you'll get that your it's going to be cosine of t times this ln of cosine of absolute value of t. So it's going to be cosine times ln of absolute value of cosine of t. And then you're going to have that plussed by t times sine of t. And then the rest of it's just your homogeneous solution. It'd be c1 cosine of t plus c2 sine of t. So it's clear that this right here is your particular solution. This right here is your particular solution. And then this right here is your homogeneous solution. And it's very clear that this particular solution is quite complicated. It's cosine of t times ln of absolute value of cosine of t plus t sine of t. There was no way you would have looked at this, and if you were to use the method of determined coefficients, came up with a solution form that looks anything like this. You may think, oh, the solution form is just a times secant of t or something. No, it's not. It's this actually. And so that's why the method of undetermined coefficients won't work only for something in general. It has to be exponential or sinusoidal or polynomial on the right-hand side. As soon as you have something different, the solution is actually potentially quite complicated, and you have to use variation of parameters. So we'll do a sort of a final example that actually is a little more involved, using both combination of reduction or variation of parameters. And then I'm going to take the same equation, change the forcing function to something also a little bit more exotic. It has an ln over e to the t. But this one, I'm going to ask you to find the Green's function and use it to solve this differential equation with a different forcing function, which is this right here. And it's just going to reuse what we did before. We're going to compute the Green's function and then take that integral from initial time to current time. And then we'll go into a little bit more theory because I got to connect this to linear independence of solutions. So I'll see you guys on Wednesday. Have a good day.